Matrices are one of the central objects we're going to be talking about throughout the entire linear algebra course. Visually, they're just an organizational tool for a grid of numbers and sometimes variables, like the one I've got here. Now, in the interest of completeness, you can have matrices whose values aren't numbers. Right? For example, in calculus, the Jacobian, which because I don't want to hear about it in the comments. I know it technically is a determinant, right? But that's something that's derived from a matrix, as we'll see a few lectures down the road here. It's made up of the partial derivatives of a function, right? With that said, for our purposes here in the linear algebra course, we're going to be interested in matrices with numeric values or things like variables that represent numeric values. So this is how we're going to connect systems of linear equations to matrices. Right? If we start with a system of linear equations and create a matrix whose entries match the coefficients of the system, we get what's called a coefficient matrix. And if we go one step further and add an extra column at the end for the constant terms, we get what's called an augmented matrix. So I've got a system of linear equations here and its corresponding augmented matrix. So to further connect these two ideas, right, let's walk through the solution of the system using both notations. Right, so first, I'll add the second equation to the third and replace the third equation with the result. Right? This simplified the system by canceling out the x1 term from the third equation. Now, if we do the same operation to the second and third rows of the matrix, we get this new result. Now, notice how this new matrix is the augmented matrix of the new system. All right, so next I'll multiply the first equation by -2 and add that to the second equation, replacing the second equation with the result. So then now we've eliminated the x1 terms from both of the second equations. Right? Doing the same operation to the coefficients and the matrix gives us a new version that, again, matches the coefficients of the new system. All right, now we can eliminate the x2 variable from the second equation by multiplying the third equation by 4, adding it to the second, and replacing the second equation with the result. And now we've almost got the result that we need for x3 in the second equation. We can get to that variable's value by dividing both sides of the equation by 11 and dividing all the equations of the second row of the matrix by 11. So finally, I'm going to switch the second and third rows to get what's called the triangular version of the matrix. So we'll be a little more specific about what that means a little later on. So from here, we could continue the process by eliminating values until we could solve for the other two variables. Or we can fall back on the system of equations and just back substitute to get the values for all three of our variables here. So that example illustrates how we can map the operations that you've already learned for solving systems of linear equations to a matching set of operations that we can perform on a matrix. Right? These three operations, replace, switch, and scale, are what we call the elementary row operations. Now, two matrices are called row equivalent if one can be transformed into the other using just these elementary row operations. It's exactly what we saw on the previous slide, right? All of those matrices that we calculated would be considered row equivalent because we used just these elementary row operations to derive each of them. So hopefully, after this lecture and the previous one, you've got a high-level idea of what matrices are and how they're connected to systems of linear equations. In the next several lectures, we're going to use matrices and row operations to derive a procedure for solving systems of linear equations that's more structured and just less intuitive than what you learned in algebra and pre-calculus classes.